All right, everybody. So this is the last section that will be on your upcoming test. And it's pretty straightforward. If you've been doing okay, kind of got your head around what we've been doing up to this point in time, then you're going to be just fine. Okay, this is not going to be any dramatic jump in terms of a complexity. What we are going to be dealing with is cases where an object can have both an angular acceleration and a tangential acceleration. All right. And so we're combining both translation and rotation with this. So we begin with this rod here, and it's a 60 kilogram bar. So that'll be important. We're going to need a moment of inertia at some point. Bars at rest on a smooth horizontal plane. So we're looking down on top of it. See the code word there, smooth. So we don't need to worry about friction. And we've got two forces acting on it there. So let's just pause and get our head around this thing for a second. So we've got a force up and we've got a force down. All right. The force that's up is stronger than the force that's down. So we expect that it's going to overcome that. So that's a difference of 60 net up, which means we have to have a net acceleration towards the top. Okay. But these guys also are generating a moment. And so we expect this thing is going to rotate as well. So we've got a net moment, we've got a net force, so we expect both angular and translational accelerations, okay? Okay, one of the things that's going to save you a lot of trouble is figuring out a good place to put a pivot point. Now, in statics, we always said that a good pivot point was somewhere that eliminated a force. Okay, especially if it's an unknown force. And that bit of advice is still good here. So in this particular case, all of our forces are known. So it's not going to really make any difference regarding where we put it, if it'll make the problem easier or not. So let's just put our pivot at the natural center of mass right here. Okay. Now this whole thing has a length of 2. And so our distances from the 20 Newton force to the center, that's a distance of 0.75 meters. And out to the other one, it's 1 meter. Okay, so we've got those two distances there. Let's go ahead and get the moment of inertia about the center of mass here. We don't need to worry about the weight because remember, we're looking down on top of this thing. But our moment of inertia is going to be 1/12 ml squared. So we've got 1/12 onto a mass of 60, and it's 2 meters long. So I is fairly large at 45. Just like that. Okay. So let's just pick one of our equations and go with it. Why don't we go ahead and pick the vertical? Okay. And it looks like I put X on all of those. Okay, well, that's kind of fun. All right, so let's turn this into F sub Y here and here, just like this. Okay, where to go? There it is. Okay. So I've got 80 pointed towards the top, and I've got 20 pointed in the opposite direction, and that's MA. There's not going to be any vertical or any horizontal acceleration here, so let's not even worry about that. So that just becomes 60 times A. And so we work out, whoa. Is the mass 60? Yeah. Okay, so that's a little odd. But so A just turns out to be 1 meter per second squared. There. Okay, very straightforward. Okay, so in the X direction, we're not going to need that. Excuse me. Let's move to the rotation because we predicted this thing should be rotating. And we've got two forces that are going to create moments. We've got our 20 Newton force, which creates a positive moment. And it sits out there at a distance of 0.7. And then we've got the 80, which also creates a positive moment. It's at a distance of 1. And that has to be I, G, alpha. Let me write in here G's. We're doing these around G, the center of mass. So then once we do some math there, alpha turns out to be 95 over IG, which was 95 over 45. And that's equal to 2.11 radians per second squared. Okay, just like that. And that's all there is to that one. Okay, and on all of these, we're going to be following this same basic procedure. A lot of times we may have to try to connect a tangential acceleration to an angular acceleration, and that's not too hard to do. I'll show you how to do that when we get to that point. But that's all there is for this one.